Welcome to this lecture. Today, let us start looking at capillary flow, which has again wide applications. Wherever you see a capillary, you could use this. I think I have formally listed down a few, so let me go forward. Before that, capillaries are ducts of very small linear dimension, okay, very thin diameter if you want to call it so, typically of the order of microns. That's what a capillary is. Capillary flows or flow through capillaries have significance in various different aspects. Some of those are microfluidics. All microfluidics, a lot of microfluidics is capillary flow. Flow through vasculature, a lot of bronchioles, arterioles are all capillaries. Flow through porous media. Okay, flow through porous media has very wide applications, whether you want to look at flow through soil, flow in wastewater treatment aspects, through beds and so on and so forth, trickle filters, or you could even look at organs as some sort of porous media in the body, or some tissues as porous media in the body, and so on and so forth. So, wide applications of these fundamental aspects that we are going to look at in this lecture. And of course, many other situations of biological interest. You are only limited by your visualization of capillaries in the system that you are working with, if there is a need. Flow through capillaries is usually laminar. Why? Because Reynolds number, rho v d by mu, velocities are usually small, the diameter is small. Okay, so diameter being of the order of microns, 10 power minus 6 meters. You'll have to, that rho v and mu, that combination needs to be very, very high for you to get into a Reynolds number of greater than 2100, because even if you consider a cylindrical capillary, capillaries are usually cylindrical. So let me just say, for completeness, cylindrical capillaries. So usually the flow is laminar, and we've already looked at laminar flow. Okay, so we'll just have to go and see what we have for laminar flow. Which aspect of it is different for capillary? How can we illustrate, or how can we bring out, the capillary nature of whatever variable that we are dealing with, and whether we can represent capillary flows through that modification. That's the strategy that we're going to use here. So let me just read this out. Thus, the equations developed earlier are applicable for flow through capillaries of circular cross section. It's good to understand some physics of capillary flows. Okay. Capillary flow arises because the force of attraction between the liquid and the wall of the capillary duct, there is a certain force. That force is called an adhesion force. That force happens to be greater than the attractive forces between liquid molecules, which are called cohesive forces. The attraction between liquid molecules is a cohesive force that holds it like this. The attraction between the liquid and the wall of the capillary is an adhesion force that is greater than this, and therefore it starts moving in the direction of this. And once it starts moving, the cohesion force takes the liquid along with the rest of the liquid. So that's what happens. So this causes the edge of the fluid near the capillary wall to rise, and due to cohesion, the liquid follows or is dragged along by the stronger adhesion as a whole, which results in the flow. So this causes the edges of the fluid near the capillary wall to rise because of the adhesion force. So because of the adhesion force, and there is a cohesion force between the liquid molecules. Therefore, the liquid follows or is dragged along by the stronger adhesion as a whole, which results in the flow. Cohesion results in a force that is usually represented as force per unit length or surface tension. Okay, so surface tension force we look at slightly differently when we analyze things. So you've already come across this, I'm sure, in your high school and so on, or higher secondary. So cohesion results in a force that is represented as force per unit length or surface tension gamma. The capillary pressure due to surface tension at that point, or the meniscus in a capillary of radius r has been already given by what is called the Young-Laplace equation. Okay. You simplify the Young-Laplace equation, you will get an expression for the capillary pressure. We are not going to do that in this course. If you are interested, or the interested students can look at J.C. Berg. There he would have derived how this comes about. The book is called Introduction to Interfaces and Colloids, published by World Scientific 2009. You can go and look at that. For now, we are just going to take that simplification and go forward. Okay. The simplification says that the surface tension, the capillary pressure due to surface tension can be given as 2 gamma, gamma is the surface tension here, force per unit length, 2 gamma by r cos theta, where theta is the contact angle or the wetting angle between the liquid and the capillary wall. Okay. Let us say it is forming a lower meniscus as water, higher meniscus as mercury. So whatever the angle between the tangent to the surface and the wall at the point of contact, that is called the contact angle or the wetting angle. Okay, that is this theta here. This is equation 3.4.2.1-1 in the textbook. This tells you that the pressure is inversely proportional to the radius of the duct. This is r is the radius of the duct. And this pressure becomes predominant in capillaries and provides the driving force for bulk flow of the liquid through the capillary, even if other driving forces are absent. Okay? Even if there is no other driving force, there is no other pressure difference, there is no pumping action or work that has been put in and so on and so forth. Even if nothing is present, just by the nature of substances, the liquid starts moving up. When other driving forces, such as those provided by a liquid column or an external pump, are present, the pressures can just be added to get the total pressure for the flow, which is minus delta P. Okay. The minus delta P, as you know, comes from a convention, PL minus P naught is delta P, and therefore you take the negative of that to give you the a part of the pressure driving force. Now, to obtain the flow rate in pure capillary, for now let us not look at these other driving forces. When no other driving forces for the flow are present, we can directly use the Hagen-Poiseuille equation. To recall, the Hagen-Poiseuille equation gave us the flow rate as a function of pressure drop. It was pi by 8 mu L r power 4, r was the radius of the pipe, times minus delta P. Okay. So that is what was the expression for flow rate. In this case, instead of the bulk pressure there, difference there, we have the capillary pressure due to surface tension. So if we replace delta P by 2 gamma by r cos theta, we get an expression for the flow rate through capillary action, okay, or capillary flow, which turns out to be, when you simplify this 2 8 go, and then this r power 4 get to r power 3, and therefore pi gamma by 4 mu L r cubed cos theta. This is equation number 3.4.2.1-2. Now, the flow rate is nothing but velocity times cross-sectional area. In the context of capillary flow, the velocity is called the penetration velocity because it penetrates into the matrix. That's probably why it's called the penetration velocity. Penetration velocity indicated by the symbol Vp times the cross-sectional area equals the flow rate. Therefore, the penetration velocity is nothing but the flow rate divided by the cross-sectional area. In this case, flow rate by 4 pi r squared. It's a circular cross-section. And if we substitute the value for the flow rate from the Hagen-Poiseuille equation that we just found, we get Vp equals gamma by 4 mu L r cos theta. Okay. You can work this out and see whether you get this. It's a straightforward thing. You could do this. You also know that Vp is nothing but dl dt, rate of change of distance with time. The distance, in this case, the distance traversed in capillary flow by the liquid, 3.4.2.1-3, and therefore you could integrate this expression to get the position of the liquid front along the capillary as a function of time in microfluidic situations, which is an important thing to know, okay, for design, operation, and so on. Okay. Now, capillary flow in porous medium. There is a medium, the flow through the medium is capillary flow. The porous media is a term that refers to any medium that has a solid matrix with interconnected interstitial spaces through which there is movement of some species of interest. So, the species of interest moves through the interconnected interstitial spaces, and it can be considered as capillary flow because the interconnected interstitial spaces are very small in their characteristic dimension. For example, soil in a porous medium through which water, pollutants and fines, etc. can travel is an example of capillary flow through porous medium. And sometimes the interstitial spaces are considered as a set of capillary tubes. We hypothesize the interconnected interstitial spaces to be represented by a set of capillary tubes in parallel. Okay, that's typically how we view the situation. We model the situation as a set of capillary tubes, and thus capillary flow through the porous media is an area with wide applications. Many substances of biological interest can be considered as porous media, as I mentioned earlier. For example, any tissue, including whole organs such as liver, kidney, heart, brain, and so on, can be treated as porous media because they contain cells that are dispersed and connected voids through which nutrients, drugs, and other substances travel to reach the cells. Okay. So, this is of direct interest to us. Tissue regeneration, which is used to grow artificial organs, typically happens on a scaffold. You all know this. We have a scaffold and then we grow cells to provide the support for the growth of cells, and then the scaffold is either removed or it becomes a part of the artificial tissue. And this system can be considered as a porous medium. The biological pollution treatment system, such as Trickling filter, or the matrix in which cells are immobilized in the type of a bioreactor, can be treated as porous medium. So, you see the applications are very wide. To obtain the kinetics of liquid movement by capillary flow into a porous medium, and that would become important when you are trying to model things to understand further so that you can use it for improved design and operation. Typically, the medium is treated as consisting of cylindrical capillary tubes. Then, the distance penetrated by the liquid into the porous medium, the distance is L. This can be obtained by the integration of this equation, which is this, dl dt equals gamma 4 pi L r cos theta. So, you take L this side and dt this side. You can integrate this, quite straightforward integration. You would get L equals gamma by 2 mu r cos theta raised to the power of 0.5 t raised to the power of 0.5. Okay. So, you have an expression for the distance penetrated by the liquid into the porous medium through a simulated capillary flow or a representative capillary flow. Okay. This is very useful. I think that will give you some idea as to how to start looking at capillary flows. This is just the starting point. How you use it is entirely up to you, according to your requirements in the future. I think we can stop here. Yeah, just the number is 3.4.2.1-4, which is important, by the way. And when we meet next, let us get into something else in momentum flux. See you then.